told you that you can actually enjoy your arm fracture. Weird, right? So, as each one of you already know, a broken arm or leg is actually treated now easily by inserting a plaster cast that the patient should keep wearing for approximately 2 months. It should be noted that the bone actually heals itself naturally. So now the problem about the solution is not the solution itself, but actually its efficiency. If you are or were a patient with an arm fracture, you're going to know exactly what I'm talking about. The patients who are wearing, of course, the plaster cast suffers from its huge weight. Suffers also from the fact that it's not waterproof, so he can't obviously take a shower whenever he wants. Also, the fact that the plaster cast is not ventilated, which actually leads to skin infection once the healing process is over. Now we are left with one important question. How might we help a patient recover from his arm fracture efficiently? Before we go any further, let's take a look on how the traditional cast is applied.
This X-ray of a Colles fracture shows the dorsal displacement and dorsal tilt. Another X-ray of the same patient shows the radial displacement and impaction. With reduction, these displacements will be corrected. The reduction will be maintained with the correct application and 3-point molding of the cast. To apply the basic forearm circular cast, the following materials are needed: a stockinette or tubular gauze bandage, cotton wool, 100 millimeters wide, will be used as undercast padding. For children, a width of 75 millimeters is sufficient. Scissors. Plaster of Paris bandage, which is available in rolls of varying widths. And water, or another wetting agent. The water should be tepid or lukewarm with an ideal temperature of between 22 and 25 degrees Celsius. It should be noted that colder water or a bandage that is wetter will allow for an increased working time, while warmer water or a bandage that is drier reduces the working time. The patient should be seated next to a table or trolley, with the elbow at the edge of the table to allow full access to the forearm and wrist. The dorsal side should face upwards, with the wrist in slight palmar flexion. This flexion will prevent the cast from sliding off when swelling subsides. The distal border is located no lower than the distal palmar crease, so that the patient is still able to flex the MP joints to 90 degrees. The proximal border lies about 2 fingers distal to the crease of the elbow, so that the patient may flex the elbow. The forearm cast should allow the patient use of the thumb, so the thumb should remain open. To begin, a stockinette is applied and cut slightly longer than the final cast will be. A small opening is cut for the thumb. A slit is cut in the cotton wool to go through the first web space and allow the patient to continue to pinch the thumb and fingers. The cotton wool is gently wound around the forearm. For a tight-fitting cast, a single layer of padding with an overlap of 1 centimeter may be used. However, this short overlap is not generally advisable. Rather, an overlap of 50% is recommended and is shown here. The 50% overlap creates a double layer of padding. Proximally, the cotton wool extends beyond the planned length of the cast, so that when the end of the stockinette is folded down, the end of the cast will be padded. The plaster bandage is dipped into the water. The end remains free, with the bandage held at an angle of 45 degrees. The bandage is held in the water until any bubbling subsides. The bandage is removed from the water. The excess water is removed by gently squeezing the ends on both sides. The application of the bandage should not begin in the first web space. Rather, it should start at the wrist with 1 complete turn. The bandage is then passed through the web space where it's gathered together. Then it goes across the palm of the hand using the full width to the base of the thumb and around the wrist. This procedure is repeated. The bandage is now wrapped around the forearm in the proximal direction, in the same manner as the cotton wool, giving an overlap of 50%. At the proximal end, a slight amount of cotton wool and the end of the stockinette should remain uncovered. The bandage is once again wrapped around the forearm, this time in the distal direction. It should be noted that although 4 layers of plaster bandage have now been applied, the shininess of the material indicates that the cast is still too soft to mold to the desired shape, that the plaster will not achieve full strength for 36 hours. The plaster is molded with pressure applied over the dorsum of the distal radius and from below onto the forearm, just proximal to the distal molding. In other words, just proximal to the fracture. The pressure at these 2 points results in the desired oval shape of the cast. The third pressure point is a diffuse area located slightly proximal to the dorsum of the radius, where the extensor tendons originate. The plaster may be smoothed with a circular motion to achieve a better fit to the forearm, taking into account the oval profile. The palmar plaster is now molded to securely fit the hand. Flexion of both the thumb and elbow are confirmed. The exercises for the patient may now be explained and demonstrated. They include full flexion of the MP joints, full flexion of the PIP joints, and placing the ends of the fingers into the palm of the hand. The forearm cast should not be too wide in the web space so that the patient can continue to pinch the thumb and fingers together. The application of the forearm cast is now complete.
First of all, we need to recover a 3D scan of the patient's arm, of course. Then we proceed by generating surfaces from the cloud of points we just recovered from the 3D scan operation, and then we get something like this. This is the surface actually generated from the points. And using the finite elements method, we can check if these casts can actually resist to the external stresses. We can clearly see how the cast is going to be deformed against the applied stresses. Of course, von Mises stresses also can be shown, and the displacements of the cast. So as a final result, we get something like this. It should be mentioned that the holes on the surfaces are there to, of course, minimize the weight of the cast. Even if the 3D printed cast is waterproof, less heavy, and ventilated, there is one more challenge left to defeat, which is the price of the 3D printed cast. So we still need to work on the price so that the 3D printed cast, our solution, is accessible to everyone.